Let me introduce you to perfect numbers, a number series known even by the ancient Greeks. These numbers are pretty special. A perfect number, when you add up all the proper factors, equals itself. For example, the proper factors of 6 are 1, 2, and 3. Summing those together results in 6, making 6 the first perfect number. The next few numbers, for those who are curious, are 28, 496, 800, 128, and the next number has 8 digits. So yeah, these numbers grow pretty quickly. Now I know you probably want more perfect number facts, or even just more perfect numbers, but one of the coolest facts about perfect numbers is their connection to the prime numbers. Prime numbers, as we all know, are the numbers without any proper factors besides 1. These numbers are relatively rare, so finding them can be a big deal. Now, one way to get prime numbers is through this formula, named after Marin Mersenne, who was a French mathematician. The formula is 2 to the power of n minus 1. So let's plug in some numbers. Say n equals 4, we get 15, which isn't a prime number. Or let's try 1, yielding an answer of 1, which also isn't a prime. The point I'm trying to get across is not every n will result in a prime, but the ones that do are Mersenne primes. Take, for example, n equals 2, 3, 5, and 7. When plugged into the formula, it gives 3, 7, 31, and 127 respectively. And indeed, all of those are prime. And all of those values of n seem pretty suspicious, because all of them are prime. And yes, in fact, n has to be prime for the formula to work. But as seen with 11, not all primes when plugged into the formula work, only some. So one interesting way to find pretty large primes is to plug a large prime number into the formula, and there is a chance that when you inspect the resulting number, the resulting number will be also prime. Now I can finally explain the connection between these seemingly separate number sequences. Every perfect number has a Mersenne prime as a factor. For example, take 6 as a factor of 3, which is a Mersenne prime. The perfect number 28 also has a factor 7, which is also a Mersenne prime. And this is a one-to-one thing, so every perfect number has the next Mersenne primes inside its factors. Now after you collect yourselves, you may want to ask, why is this true? Okay, so now the next thing we need to find out is the factor between the perfect number and the corresponding Mersenne prime. For 6 and 3, the factor is 2. And for 28 and 7, it's 4. Writing a couple more of these, the pattern is not obvious, but there is one. They are 2 to the power of 1 less than the input for the Mersenne prime function for that corresponding prime, or n. And yes, that's a mouthful, and let's prove why it's true. So this number 2 to the power of n minus 1, and this number 2 to the power of n minus 1, trust me, there's no confusing them, when multiplied together, we get a perfect number. So the factors should add up to itself, or for this proof, twice itself, since we are actually not going to just use the proper factors, but also count itself as its own factor. For 2 to the power of n minus 1, the factors are following: 2 to the 0 plus 2 to the 1, all the way up to 2 to the power of n minus 1. Simple enough. Now the prime part 2 to the n minus 1 also factors into play. So we add 2 to the n minus 1 times 2 to the 0 plus 2 to the n minus 1 times 2 to the 1, so on and so forth, all the way to 2 to the n minus 1 times 2 to the n minus 1. And now we're going to try to simplify this sum. We can factor out the 2 to the n minus 1 to get 1 times 2 to the power of 0 plus 2 to the power of 1, and so on and so forth, all the way to 2 to the power of n minus 1, plus 2 to the n minus 1 times that entire sum again. Simplifying further results in 2 to the power of n times yet that sum again. The right side, the sum we've been talking about, seems like it would be tricky to actually add up. So let's just call it a. If we multiply a by 2, we get 2 to the power of 1 plus 2 to the power of 2 all the way to 2 to the power of n. All the powers just get added up by 1. So when we subtract a from 2 to a, which will equal just regular a, this results in 2 to the n minus 2 to 0, or just 1. So the right side of the equation, the sum we've been talking about, is just a delightful 2 to the n minus 1, making the complete total sum 2 to the power of n times 2 to the power of n minus 1. And remember, this is twice the original, which is, we're proving, is going to be a perfect number. So the original is 2 to the power of n minus 1 times 2 to the power of n minus 1. And that is what we originally said it was. And so it is a perfect number. I made sure to specify in chapter 3 of this video even perfect numbers. And that's because at the time of this recording at least, odd perfect numbers have not been proven to exist, or disproven But if they did exist, they wouldn't exhibit this magical Mersenne primes and perfect property. But anyway, thanks for watching.